Black holes, those enigmatic cosmic entities formed from the gravitational collapse of massive stars, have long captivated scientists and the public alike with their profound implications for our understanding of space, time, and reality itself. At their core, black holes are regions where gravity is so intense that not even light can escape once it crosses the event horizon, the point of no return. However, theoretical physics has speculated that these seemingly destructive voids might not be the ultimate endpoints of matter but could instead serve as gateways or portals to entirely different universes. This idea stems from Albert Einstein's general theory of relativity, which describes gravity as the curvature of spacetime, allowing for exotic structures like wormholes, hypothetical tunnels that could connect distant points in our universe or even bridge to parallel ones. While no empirical evidence directly supports this notion, advancements in quantum mechanics and cosmology have fueled ongoing debates, suggesting that black holes might harbor hidden pathways beyond our observable cosmos. For instance, if a black hole's singularity, the infinitely dense point at its center, could be resolved through quantum effects, it might open up to a new realm rather than crushing everything into oblivion. This speculative framework challenges the traditional view of black holes as mere gravitational traps and invites us to reconsider their role in the grand architecture of the multiverse. The concept of black holes as portals often traces back to the Einstein-Rosen bridge, a mathematical solution to Einstein's field equations proposed in 1935 by Albert Einstein and Nathan Rosen. This bridge, essentially a type of wormhole, was initially envisioned as a connection between two separate regions of spacetime, potentially linking our universe to another. In the context of black holes, the Schwarzschild metric, which describes non-rotating black holes, reveals a structure where the event horizon conceals a bridge that, in theory, could lead to a white hole, a hypothetical object that expels matter and energy, the reverse of a black hole. However, early models showed these bridges to be unstable and non-traversable, collapsing almost instantaneously under their own gravity, making any journey through them impossible for matter or information. Despite this, the Einstein-Rosen bridge laid the groundwork for modern theories, illustrating how black holes might not be isolated but interconnected with other cosmic domains. Over the decades, physicists have refined these ideas, incorporating quantum fluctuations that could stabilize such structures, turning what was once a mathematical curiosity into a plausible, albeit unproven, mechanism for interdimensional travel or universe hopping. One major hurdle in viewing black holes as portals lies in the traversability problem, where the intense gravitational forces and tidal stresses would likely destroy any object attempting to pass through. In general relativity, wormholes require exotic matter with negative energy density to remain open, a substance that defies known physics and has never been observed. Traditional black holes, with their event horizons, trap everything that enters, leading to the infamous information paradox, where quantum information seems lost forever, violating unitarity in quantum mechanics. Yet some theories propose that quantum gravity effects, such as those in loop quantum gravity or string theory, could avert singularities and create bounce scenarios, where collapsing matter rebounds into a new, expanding universe instead of being annihilated. For example, in models where black holes evolve into white holes over immense timescales, the interior could act as a conduit, expelling contents into a fresh cosmic expanse. This resolution not only addresses the paradox but also posits black holes as birthing grounds for new universes, an idea that aligns with inflationary cosmology's multiverse hypothesis, where our universe is just one bubble in an eternal sea of expanding realities. Rotating black holes described by the Kerr metric introduce additional intrigue to the portal hypothesis, as their spinning nature creates a more complex internal structure, potentially allowing for safer passage. Unlike static black holes, Kerr black holes feature a ring-shaped singularity and an ergosphere, where spacetime is dragged along with the rotation, enabling phenomena like frame dragging. Theorists like Roy Kerr himself have speculated that these rotations could prevent the formation of a point singularity, instead forming a navigable path through the black hole to another region of spacetime or universe. In such models, an infalling observer might avoid the singularity by passing through the ring, emerging in a different universe with possibly inverted properties, such as anti-gravity or reverse time flow. However, the Cauchy horizon, a secondary inner horizon in rotating black holes, poses instability issues, potentially turning into a wall of fire due to accumulated perturbations. Despite these challenges, simulations and analytical studies suggest that with sufficient spin and minimal charge, these black holes could mimic stable wormholes, offering a theoretical loophole for portals. This has implications for astrophysical observations, as many detected black holes, like those imaged by the Event Horizon Telescope, are rapidly rotating, hinting at untapped portal-like behaviors hidden in their dynamics. Renowned physicist Stephen Hawking contributed significantly to the discourse by proposing that black holes might provide escapes to other universes, particularly in resolving the black hole information paradox. In his later work, Hawking suggested that information entering a black hole isn't destroyed, but could be encoded on the event horizon and potentially leak out via Hawking radiation, virtual particles that become real near the horizon, causing the black hole to evaporate over time. Extending this, he theorized that supertranslations, subtle shifts in spacetime around black holes, could store this information, allowing it to tunnel to alternate universes rather than being lost. This soft hair on black holes, as he called it, implies that what falls in might re-emerge elsewhere, perhaps in a baby universe branched off from our own. Hawking's ideas, presented in papers and lectures up to his passing in 2018, bridge quantum mechanics and gravity, suggesting black holes as multidimensional gateways where information conservation demands portals to preserve physical laws. While controversial, this framework has inspired subsequent research, emphasizing that black holes aren't information sinks but dynamic interfaces between realities. Nikodem Poplawski's torsion-based theory offers a compelling alternative, positing that black holes connect to other universes through repulsive gravitational forces at extreme densities. In his 2010 model, torsion, a twisting of space-time predicted in Einstein-Cartan theory, prevents singularity formation, instead creating an Einstein-Rosen bridge to a white hole in a new universe. This implies that every black hole in our universe spawns a daughter universe inside it, with our own cosmos potentially originating from a parent black hole's interior. Key to this is the Big Bounce concept, where collapse halts and reverses into expansion, aligning with cyclical universe models over a singular Big Bang. Poplawski argues that torsion, unobserved in weak gravity but dominant in black holes, keeps physics finite and allows matter to pulsate through portals. While lacking direct evidence, the theory gains traction from cosmic microwave background anomalies and the universe's possible closed geometry, suggesting we inhabit a vast black hole hundreds of billions of light-years across. Critics point to torsion's elusiveness, but supporters like Nick Gorkavi see it as an elegant resolution to cosmological puzzles. Superstring theory elevates the portal idea by incorporating higher dimensions and branes, where black holes might serve as conduits via S-branes, space-like hypersurfaces that emerge when curvature reaches string scales. In a 2021 proposal, an S-brane inside a black hole's horizon induces a smooth transition to a new universe, resolving both black hole and Big Bang singularities simultaneously. This framework views black holes as creative engines, birthing young universes that evolve independently, potentially mirroring our own with stars and life. By unifying quantum and classical physics, string theory allows for stable portals without exotic matter, as strings and branes provide the necessary structure. The model predicts that passage through such a portal would be one way, with the new universe expanding from the influx of matter. Though mathematical and awaiting empirical validation, it harmonizes with multiverse theories suggesting an infinite hierarchy of universes nested within black holes. Peer review and further simulations are needed, but it represents a bold step in quantum gravity. Recent 2025 studies have bolstered the mimicry hypothesis, showing that some black holes could be wormholes in disguise, indistinguishable through current observations. One investigation into quasi-normal modes, space-time vibrations from perturbations, found wormholes replicating black hole signatures across scalar, gravitational, and electromagnetic fields, suggesting exotic compact objects beyond general relativity. Another explores black holes transforming into white holes via quantum fluctuations, linking time's arrow to dark energy, and proposing portals where singularities give way to new beginnings. Scientists like Stefan Gielen and Lucia Menendez-Pidal argue this resolves unitarity issues, allowing observers to theoretically traverse to white holes. These findings, published in prestigious journals, highlight how wormholes might form from stellar collapse if quantum effects intervene, evading event horizons. While computational challenges persist, they fuel excitement for gravitational wave detections to differentiate true black holes from portals. The portal concept has profound implications for the multiverse, where black holes could seed infinite realities through eternal inflation or branching quantum events. If each black hole births a universe with slightly varied physical constants, it explains fine-tuning for life in ours, as we're in a habitable bubble among many. This also tackles the information paradox. Without horizons and wormhole models, information flows out unimpeded, preserving quantum coherence. Critics argue that forming stable portals requires implausible exotic matter, and observational data from LIGO or the James Webb Space Telescope show no anomalies suggesting portals. Yet, theories like those from Thibaut Damour and Sergei Solodukhin propose wormholes mimicking black holes so perfectly that only microscopic experiments, such as particle accelerators creating tiny black holes, could distinguish them. Wormholes lacking measurable Hawking radiation. In conclusion, while the idea of black holes as portals to other universes remains firmly in the realm of speculation, it is grounded in rigorous theoretical physics and continues to evolve with new insights. No direct evidence exists, and practical traversal seems impossible due to extreme conditions, but mathematical consistency across general relativity, quantum mechanics, and string theory keeps the possibility alive. Future observations, from advanced telescopes probing black hole interiors to potential quantum gravity breakthroughs, may one day confirm or refute these portals. Until then, black holes challenge us to expand our cosmic imagination, reminding us that the universe's deepest mysteries might hold keys to realities beyond our own.